So today's lecture will be about actor critique networks. Okay, so you remember the taxonomy that we studied where we have MFRL and the three types were value based, policy gradient and actor critique, right? What were the types in value based? Anyone? Raise your hand and tell me. Yes. Monte Carlo and TD. Okay. And then you have policy gradient, right? And then in policy gradient, which algorithm did we study? Reinforce. Reinforce follows MC or TD? MC, right? So today's lecture will be about actor critique. Actor critique is in fact the most important method when it comes to using RL as a controller, okay? Because of the structure and because of the way actor critique algorithms work, it is one of the most applicable or the most useful algorithm for solving control problems using reinforcement learning. Clear on that? Okay? Okay. So value based, we had one thing to do, that is to compute the value function, and based on that we then extracted the optimal policy, right? Which would, from the way it works, you understand that it is difficult for continuous problems, right? Because as the number of states and actions increases, the table or the Q table that you formulate in order to pick the best action becomes prohibitively big, right? So you don't want that to happen. So instead, you then relied on policy gradient methods. In policy gradient methods, you did not find the value function explicitly, rather you simply took actions, saw the returns and then tuned the actions such that the actions with the best returns, the probability of that were increased. Clear? Right? So now we see that there are a few drawbacks in policy gradients as well, right? What were the drawbacks? The variance was high and we had to wait for the entire episode to complete, right? Because with any Monte Carlo approach, that is a drawback, that you have to wait for the entire episode to complete or roll out, and then you could take this rewards from that, the returns from that, right? Value based kind of negated that by using something called expectation of the returns using value functions, but it was not good for continuous functions. So then the third paradigm of RL comes into play in this regard, that is it combines both policy gradient and value based methods, okay? By combination of these two, what do we mean? We mean that there is two components in actor critique. Just as the name suggests, there is an actor, there is a critique. So it involves both optimizing the policy directly as in policy gradient and evaluating the value function as in value based methods, right? So the actor is responsible for policy gradient part, right? Whatever the policy gradient did separately, the actor does an actor critique. Whereas the other one, you have, what do you say? The critique does the work of the value based part because it simply evaluates how good or bad that actions were, right? Based on this, we will build towards deep reinforcement learning using function approximators, okay? Okay. So what was one of the major problems in reinforce, that is policy gradient method, was you had to rely on the entire episode to complete and the variance was pretty high, right? Because the episodic returns changes drastically one episode to the other, right? That makes the learning unstable, right? So you wanted better mechanism for that. So remember in the expectation equation for the gradient computation reinforce, you had an equation something like this, where you take the derivative of the log of the policy, right? And then you multiply it by the returns from that point onwards, right? So what is done here is, you simply take a baseline and subtract to see not the full return, rather the difference in the expected return that you would get and the actual return that you're getting, okay? So what did I just say? You're trying to find the difference between the actual return and the expected return, right? By the word expected return, what do you understand? What does this give you mathematically? the value function, right? So this part, so the ideal baseline would be the value function here. So this term would simply then become an advantage term, like how good or bad that actual returns were compared to the expected returns, right? Clear? 100% clear up until this point? Okay. So just as I stated, the actual returns minus here the baseline, ideal baseline would be a value function, okay? So you can simply say by seeing the value of advantage, whether it's positive, negative or zero, whether that returns, whether that actual policy that you followed was better or not, right? If your returns are higher, that difference would then be a positive number, right? Implying that the actions you took were better than the expected policy, right? So here it says actions did better than expected. When actions do better, what do you do in policy gradient methods? Exactly, you increase the probability of taking that action, right? However, if that difference is negative, that is the advantage is a negative number, then what do you know that the policy did not do good compared to the expected policy, compared to the expected rewards, right? In that case, what will you do if the actions did not perform well? Decrease the probability, okay? If it is zero, there is no change. It means that the actions that you took is exactly the same that you expect from the policy, okay? Zero advantage basically. Clear on this? So therefore, the resulting policy update now, instead of GT, you have AT. AT is the advantage term. Got it? Clear? So this is the central idea of actor critique methods, okay? You had the value function was estimated by the critique, and the actor will update the policy parameters based on just the advantage. Clear? Yes. Sorry?
What is the difference between A and B? I mean, it's written as equal. The previous slide was written A equals B5. Yes.
A is the difference between the returns, actual returns. GT is the actual returns. V is the expected returns. So that will simply tell you how good or bad your actions were compared to the expected value function.
It's treated as an error, right?
Yes, that's a very good point. In fact, you will see later on when we are computing the loss functions, this AT is nothing but the TD error, right? Yes.
So the disadvantages of value-based
Uh-huh.
approach for continuous action
Yes.
based problems, it still remains. So why are we using it for the critique?
What do you mean? Which?
For actor critique method, for the critique part, we are using elements of the value.
Yes.
So a value-based approach.
Okay.
Yeah. So we said that we moved on to policy gradient method because in case of continuous steady space, value-based methods are not good. So, but now it still remains.
Okay.
Why?
Okay. When we say that we are using value-based methods, it means we are using value-based methods end-to-end. In the sense, it involves two stages. What are the two stages? Policy evaluation and policy improvement, right? Policy evaluation is fine, you can do it because you're simply using expectation. The difficult part with value-based functions is the policy iteration part. So, sorry, the policy improvement part. Because for that, you need to rely on this table, and then you have to take the best actions corresponding to your states, right? That part you're still not doing in value-based. The critique simply evaluates the policy. It is the policy evaluation that is done by the critique, not the policy improvement, okay? For the policy improvement part, then we go to the actor, which does it through the policy gradient method. Clear? So that's why we have value-based method component and policy-based component in it, policy gradient component in it. Clear? Okay. So yes. So now when this actor critique method is to be optimized, or we have to obtain an optimal policy using actor critique method, as you understand, there will be two set of parameters. One will have to do with the value function, The other will have to do with the, sorry? Yes, the probabilities of action, which is the policy, right? So you have one set of parameters for the value function, that is critique, the other set of parameters for the actor or the policy, okay? So here, how does it work? See, you take an action, okay, from the policy that you have, see the return that you get, and obviously like this, as I said, remains constant. This tuple you have of S, A, R, S dash or S prime will be constant throughout reinforcement learning, right? Because this is the sample that you are taking. Since you do not know the environment dynamics, you have to now rely on samples, right? So that's why this is a very important component of reinforcement learning algorithms, okay? So exactly here, now if you are in state S, you take an action A, then observe the reward and the next state, right? You do not compute it because you don't have the model, you rather observe whatever the reward and next state is. Clear on that? And then based on that, what is this? This is the TD error that you're computing, okay? However, this term that you have here, tells you what? Immediate reward plus the discounted future reward, okay? Now assume you take 5 steps and then you take the future reward. So then it would be R1 plus R2 plus R3 plus R4 plus R5 plus gamma of VS6 basically, right? If you keep increasing the n here, what does this term become? Sorry? It will be a value. What value? Like, I mean, if you increase the number of R's here to infinity, complete episode, which is nothing but the return here, right? So this would be GT minus V. We saw it somewhere else as well. What was that? Advantage function. So in fact, when you have this thing, when this entire episode runs, this TD error becomes the advantage function. Clear? I hope this is erasable. Shouldn't have done it, okay?
Just remember, W move, it's written as a parameter value function.
Yes.
The way to
Okay, when we move towards deep reinforcement learning or when neural networks come into play, then that W becomes the weights of the neural network. However, for now it is any parameter. Whatever you're using, either a linear function or a non-linear function or simply numbers, your W is just the parameter of the critique, okay? Okay, so what are we doing here? W, that is the parameters of the critique, has to be updated such that this error has to reduce. Why? Because when that error reduces, we know that the expected value function is similar to the actual return that you're getting, right? And you will update theta accordingly, right? Based on how good or bad your policy is, because that's now an advantage function as well, right? So based on that advantage function, you will update theta, which is the actor parameters. Clear? Okay. This error that we have, we write it in this term now as a loss function, mean squared error, okay? Because we have to take the derivative later on to compute the gradients. That's what it is. And then based on that loss function gradient, we then compute the updated W's or the parameters of the critique. Clear? Similarly, for actor, we do the same thing, right? We take the gradient now of the policy. Remember, when we are working on policy gradient, the gradient is on the policy, not the value function, right? You take the gradient and then you update the expected theta accordingly to increase the probability of the good action or the better action and decrease the probability of the bad action, okay? Now, again, this is just the overview of the entire actor critique algorithm that we'll be using, okay? Now, with this actor critique methodology as the baseline, there are different algorithms. Okay. Firstly, one being called A2C, advantage actor critique. Okay, it stands for A2C, right? So here, from the name, you understand that it uses actor critique and it uses the advantage function, which is nothing but your TD error, right? See, you take the expected returns here, okay? And also, what was that? We had this value, remember, for TD, RT plus gamma times V of S prime. Yes, we had this, okay? This also equals to what? Q value, right? This is Q pi as well. So that's why we can use Q pi there. Because if we don't want to wait for the full episode, we could take this value. If we wait for the full episode, this becomes GT, right? However, for TD approach, where the number of steps you take is less than infinity, then this would be TD approach, where you will use Q pi and not GT. Okay? Clear up until this point? Sure? Okay. RT. RT plus gamma V S prime. V pi of S prime. Okay? So again, this is the derivation here where you take the actual returns minus the expected returns, that is the value function, and you use that as the advantage. So now you're bootstrapping, right? GT bootstrapped will be this equation that we have here, R plus discounted future value of that state, right? You substitute that here, you get an advantage function here now, and then you update the parameters of theta accordingly. Okay. So you see here now, actor learns from critique, right? In the sense that the critique is the guiding factor here, how good or bad that is. Actor will take action, critique will then evaluate it, right? So in that case, what is one of the key requirements is the learning rates that you have for critique should be higher than your actor. That means your critique should learn at a faster rate than the actor. Why? Yes, okay, yes, critique will guide it, okay. So how this happens is, your actor generates a certain policy, okay. The actor will follow that policy, okay. Now say if the actor updated its policy before the critique gives its feedback, and the actual policy that the actor gave initially was better, it cannot revert back very easily back to it. Again, it will have to go through some iterations, right? So that is why feedback is more important, and it should be faster. Right? Yes.
Faster in a way that it should be done in a step before.
No, the rate should be faster. You cannot do it before, then it will be non-causal, right? Because then you will try to evaluate something before it happened, which cannot happen, right? So it is simply the rate at which it is happening should be faster, in the sense that, say, the actor cannot update its policy 5 times while the critique has updated or evaluated the policy only once, right? The other thing is still fine, in the sense that the critique can evaluate the policy 5 times, but the actor generates only one policy in that time. Clear? Clear? Sure? Okay. This is just a summary table here, okay, which says, so now you have, if you use policy-based method, the variance is high. With value-based, variance is low. In actor critique, because it is a combination of those two things, it's moderate, right? It's not very high, it's not very low. Similarly, in policy-based methods, or in Monte Carlo approaches, like reinforcement, you do not need any bootstrapping, because you wait for the entire episode to roll out and then see the returns. However, with TD learning TD learning, you do not have to wait for the entire episode. You simply bootstrap the estimates later on, right? In actor critique, because it relies on estimation, there is bootstrapping involved. Okay, clear? And yes, policy gradient methods can be used for continuous spaces. Value-based methods, no. Actor critique, yes again. Okay? You understand, right? Why we can, why we cannot use it? Okay. So just like the classical TD approach where we had TDN as well, where you could see the number of steps you could take as returns and then estimate the value, even here, even in actor critique methods, you can do exactly that thing. You have n-step bootstrapping. Say you don't want to bootstrap the entire episode. Like you want to say take 10 steps and then you want to rely on bootstrapping. You can do that, right? So that n depends on the number of steps you will take before you estimate the value function from there on. Clear? This is simply to trade off the bias and variance, which we already talked about, right? Right? Okay. Why is there no feedback today from no yeses, no nos? Okay. Yes. This synchronous advantage actor critique comes into play when you're working on computers, right, which have multiple cores maybe. Okay, so in that case what happens is you can run the agent parallelly in multiple cores and they each will update the global parameters as they interact with the environment. Okay, that is, say you're working on a team project, okay, and then you make a Google document somewhere. So now in synchronous advantage actor critique, what you do is synchronous A2C, that is, as soon as one member of the team completes some part of the project, he'll directly update the main Google document, okay, the shared document for the entire team. And then the other one will again update it as soon as he does it, the main document, okay. No individual workers will have, no individual team members will have their own copy of the document. There is only one global document which is updated by everyone as they complete it. No. No, in multi-agent reinforcement learning, you have multiple agents interacting with the same environment at one time. Here, you have one agent interacting with one environment. Again, you make a copy of that agent and environment. Again, you make a copy of that agent environment. So there's one agent, one environment. Or rather, there's one environment, one agent interacting in that environment, but in different ways. So basically, you are evaluating multiple policies at the same time to speed up the learning because you have multiple cores, right? Yes.
So regarding this point, so previously the RL runs on GPU. This was like, because I hear about it in the media. When doing it actually, I discovered actually the RL part runs on the processor only, maybe the neural network only runs on the GPU. Then how to optimize it on CPU? I mean, this one method, but I mean, is it like only for A2C or algorithm specific or like a general way to make a parallel environment for training?
No, with any standard library you're using, you could parallelize it, right?
And this makes it faster?
This makes it faster, yes. Because see this real life scenario where say if you want to learn driving, okay, you're learning only once on one car. It'll take you say 10 days, okay? But hypothetically, you are able to make a clone for yourself, okay? And you have and the clone is again in a cloned world of the same world that you are living in, okay? Now, but somehow magically, all your clones can share their information in one place, right? So now, say one day, your one clone learns reverse parking, the other clone learns, say, parallel parking, and the other one, say, learns a U-turn. All of them together can combine this information, and then instantly, after one day, you have learned 3 skills, right? But it's not different skills that you're learning here in synchronous A2C. You're learning one skill, but then you're trying different policies.
Does it have the same effect as increasing the time steps? Because I noticed sometimes when I trade, like for example, 1,000,000 time steps, where this is okay, or like reach the point.
Okay.
Then I try, why not 6 million and wait? The word could walk almost stable, then sometimes it tries to drop.
Okay.
Like it gets worse sometimes when the time steps goes up. So like, what is the limit here? Thinking Like, if it's the same as 5 steps to see where it separates?
No. It is independent of the time steps. Okay? Time steps is simply the number of samples you can collect at one time, in that one episode basically. Okay? Or the summation of all the episodes that you took. This one is same episode happening parallelly but with different actions, with different policies. Say you have 5 policies, or rather 4 policies, and you have a 4-core computer. So every core can run one copy of this environment agent, and it's like, okay, fine, I took actions. Say you have a policy with 5 actions, A1 to A5, okay? But yes, A1 to A5. Policy P1 is this thing. P2 will take this. P1 will take this in order. P1, 2, 3, 4. 2 will be say 1, 3, 4, 2, 5. This will be 5, 2, 4, 3. So basically there are different policies. And then they're like, no, if after 1 I take 3, it is better. And then I take 5, it is better. Then I take 2, it is better. You see? Because they are all running parallelly, they will execute different policies in the same environment by the same agent. Okay? And then based on this feedback, they will update the actor and critique parameters. Okay?
Why we are using it because of the slowing down the convergence time, like between fast and convergence?
Yes. Yes.
That's why we are
Yes.
using it.
Yes.
In a program, the computation time is higher, so we will implement this.
Yes. Yes. There is another version of this, asynchronous advantage actor critique. Okay, this is A3C. In this, every agent will have his own copy, its own copy of the parameters. It will update the parameters individually, and then say after n number of episodes, it will update the global parameters, right? So from that, you see that if all the people are simultaneously making changes, while one is already working on something, the other updates it, it's not very stable, right? The changes can vary drastically because say you write an equation, your friend again will write some other equation within that same section, and then you both realize it's wrong, so you change it, again you do it. So that is very unstable. However, this one, individually you write your own copies of documents, you meet once a week and you're like, okay, fine, this part is good, this part is good, this part is good. Let's all compile this parts, the good parts in one document, right? And then again we'll go back, iterate over it, and then improve the entire document. Similarly here, you're doing exactly that. Every individual agent gets its own copy of the parameters, and it will update that after say n episodes or n number of time steps. It will go and it will update the global parameters of the actor and critique, right? Okay. In synchronous, what you have is every individual agent, when it's interacting with the environment, it gets a feedback, right? Whether it's good or bad. And then what do you do in actor critique? You change the critique and actor parameters in order to get whatever the optimal policy you want, right? In synchronous one, the first one that we studied, there in that method, everyone has to update only one global set of actor and critique parameters. They do not have individual copies. In asynchronous, every agent has its own copy of parameters. It will be like, okay, fine, say suppose, again, like a group project, like I said, okay. Now if I tell you to do a derivation of certain equation, okay, and I tell you you have just one board, this is your team, I make 4 teams, okay. One team come and writes the updated equation here. The other one is like, oh no, this term is wrong. When you're writing that equation, they'll be like, no, rub this term, add this term here. Because you only have one global parameter copy here, right? However, if I tell you that, okay, make 4 teams, each one of you do the derivation, then come discuss with me, and then again I'll give you feedback. Based on that, you will update it. You get it? Every member has its own copy, it will update the parameters, and then later on, say after certain episodes, n number of episodes, it will update the global parameters. This will stabilize the learning, right? Clear?
When we will use the synchronous advantage activity, or when we will use the asynchronous activity, what will be the program, what we will apply?
Okay, I will revert back to my standard answer that I have been giving for all these questions. Depends on your application and what kind of output you're expecting, right? Say you have a CPU with a lot of cores. Use asynchronous methods. because everything will individually update its own parameters, and then with say after 10 episodes or 100 episodes or whatever, it will update the global parameters. That will be more stable and faster. Right? But the same argument holds true even for synchronous as well. You could do the same thing for that. But then the learning will be unstable in that case. Right? So say suppose you have 12 cores, okay? You have 12 cores and then you have synchronous method. So imagine 12 people trying to update one thing at a time. The learning will be very unstable, right? So A3C will negate that, it will make the learning more stable and efficient.
Efficient based on computation or
Yes, based on computation time as well in a sense. Okay, but again this does not hold true for all applications, right? For let's say most applications. Okay? Any questions, anyone? Okay. Yeah, this word correlation that you see here, we'll be talking about this in detail a little bit later. But then, okay, what is correlation here in the sense that you take an action, okay, you remember when we were talking about the reinforced algorithm where we have the term GT and not G0. What was the difference between having G0 and GT? You remember I told about G0 and GT. So your gradient that you're computing was pi times GT, right? And not G0. G0 means all your rewards total. GT means it's starting from some time from there onwards, right? We are using GT and not G0. Why? There was a word I talked about. Yes. Sorry?
G0 is constant.
No. G0 as in G is from the starting. G0 is not a constant.
Evaluate each action.
Exactly, credit assignment, right? Because that helped us in credit assignment. Remember credit assignment where you were back propagating the returns that you get? Okay. Similarly here, what happens is, so remember in that when I gave you an example, a few actions were good, but few actions weren't good, right? So if you have a correlated experience, okay, what you do is this entire series of actions, you will judge them as a series together. You correlate all the actions to one another, right? You do not decorrelate it. Got it? So that is one of the issues in synchronous methods. However, with asynchronous methods, that is broken. Why? Because they individually update their parameters and then they come together, they update the global parameters based on their individual updates. Okay, so when you have individual agents working on a policy, if the updates are happening in a correlated way, it means that the entire series of actions that you have in that policy will be judged in the same way. There is no credit assignment to every action happening, right? Right? So now you want to decorrelate these experiences, that is, you want to make these tuples individual, right? In one episode, say you have 100 such tuples, okay? You will not consider them individually, you will not group them all together and then update your parameters. What you do is you take just one tuple and based on that you will update your parameters. So you're cutting the temporal relation that you have between the states there, right? In that way you will know exactly which action to take in which state, right? Because what is this telling you at the end? The most important thing is the action here, right? Reward and its next state is just the observation, right? So the observation that you have is for the action, right? So for one state, no matter what next action you are taking, there might be a good action that you have taken in that state, but the next actions might be bad, right? Which would end up in you getting a lower return for the entire episode, right? So this way, if you judge simply the final return that you're getting, you have a temporal relation between these tuples now, right? You don't want that to happen, right? For more efficient learning, you simply want to know which action, in which state, what reward.
So temporal relationship, that is
Asynchronous. Asynchronous.
Okay, you lost me. Like, so synchronous, they obviously, all of them, they look at the very same.
Yes.
Like,
Parameter
they
copy.
are trying different policies.
Yes.
And synchronously applying the best of them.
No. At every iteration, you don't know what is best, right? You're simply tuning it towards the best. You get the point? Okay. Okay, again, if you tell me again, I'll explain you based on that. Go on.
Honestly, I got the explanation that he says vis-a-vis synchronous as opposed to asynchronous, but like how it works and
The correlation
that's
part.
the advantage. Like if we are trying different policies with as far as synchronous goes, okay. So which policy do we apply? And quite honestly, right now I'm not sure how asynchronous is different.
Okay. When you have synchronous, you have a policy pi main, okay? Let's say pi m, okay? There are different agents. Everyone get a copy of this policy, okay? They're running the same policy. But remember, these policies are stochastic, right? And also, for every state, there are n number of actions. Assume there are n number of actions, right? So you can, okay, even if you assume that it's taking the same actions.
Stochastic, meaning you have
The transition.
or
Transition,
dynamics.
yes, the transition dynamics, okay? So say every one of this policy, let's assume for the sake of explanation here, is A1, A2, A3, A4, okay? This entire policy is of 4 actions. And obviously it corresponds to S1, S2, S3, S4, okay? So here you're in A1 now, you're in S1, your policy tells you that if you're in S1, take A1, okay? You take A1 here. The transition probability is 80% in S3 and 20% in S4, okay? This is agent 1, this is agent 2, okay? Both of them take A1, okay? This ends up in S3, this ends up in S4. With the same action now, you go to different states, which would in turn result in different returns or the expected value functions.
Because of the transition probability.
Because of the stochasticity, the transition probabilities, right? So at the same time, you are able to evaluate the same action now, right? For different possibilities. And then based on these, say S3 is a bad state and S4 is a good state. So this agent 2 will tell that this action A1 that you took, increase the probability for that. Whereas agent 1 will tell, no, because I ended up in a bad state, this action is bad. So do not take this. So reduce the probability of this. So you see how this is happening at the same time, same action, because they are working synchronously, based on what rewards they are getting, they will tune the parameters such that, and the value function will also change here, right? Like say the value function here, both of them will tell, okay, this A1 will tell the value is bad, whereas A2 will tell, no, the value is good. So you see how unstable that learning becomes? Whereas with asynchronous, A1 will get a copy of pi m, A2 will get a copy of pi m, or they can formulate their own pi's, okay? And then they form this tuple here, and then they are like, this series of tuples that I got for this episode resulted in this returns. And obviously you have the stepwise reward as well. And then based on these, it will go and update the policy now. They're like, see, listen, I took this actions, this is what I got. And then agent 2 will be like, okay, I took almost similar actions, but I got this. So then they both will mutually say they have, for A3, say assume A3, no matter what, it always ends up in S2, which is a good state. So then they both will agree at that time that, okay, A2 has 100% has to be increased. But A1, A3, okay, let's not increase it, let's not decrease it by much, but by say the number of agents you have, say you have 6 agents and 4 of them tell it's good.
Now you're talking synchronous.
Asynchronous, yes.
Asynchronous?
Asynchronous, because they individually ran their copies, right? And then they already updated the parameters a little bit. Say after 10 individual updates, they go and update the main parameter. Because within 10, you get some kind of stability, right? You'll be like, okay, fine, this set of actions, I repeated it 10 times, it was good. For me, I repeated it 10 times, 8 times it was good. The other one will say, okay, 6 times it was good, overall you know that that action is good because it has already been tested by the individual workers enough number of times. So then that way the update that is happening is more stable as opposed to this one, because in this one,
It's messy, but how would we resolve that mess?
which one?
Like with synchronous.
That's why we have asynchronous. A3C.
Yeah, but we still can apply synchronous, right?
So why asynchrony helps? Because it obviously explores diversity. So now you have more exploration. Every agent will do its own policy, run it many times, right? And anyways, choice policy gradient methods are good at exploration, right? We already saw that. Okay. Replay buffer. Okay, we'll come. Okay, replay buffer is nothing but this thing, right? This tuple that you have. What you do is you simply put this tuple in a box, right? You take whatever, you run a policy, you get say 100 tuples for that one episode, you put that in a bag, you put that in a bag, that bag that you have is called the replay buffer, okay? And anytime you want to update the parameters, and if it is off policy, you can simply take one tuple from that box randomly and update the parameters, okay? Yes?
This on policy, there's no need to use the
Replay buffer, yes. Because that time it's of no use. You cannot update the parameters based on policy that you have not followed, right? Clear? However, you see here as almost a generalization, off policy methods are more sample efficient than on policy. Why? Because you can reuse the samples, right? This replay buffer is basically a reusable bag, not a dustbin, right? It's not a trash bag, it's a recycle bin. So in the sense that if the thing goes inside, you can take it out and actually reuse it again. Whereas in on policy methods, once you have a tuple and it goes in that box is a trash bin now, finish. It cannot come out from that, it's of no use now, right? So one sample, used once, wasted, that's it. Off policy, no, you can use it n number of times. Yes?
Actor critic methods
Actor critic methods are
are off policy.
off policy. No, in actor critic actor critic is a general paradigm within which you have many algorithms which may or may not be on policy or off policy.
Like every one of them has
Exactly. Like SARSA and Q learning, on policy and off policy. Even in actor critic, you have multiple algorithms which could be based on how you implement it, either on policy or off policy.
policy gradient as well.
Policy gradient as well, yes. Yes, policy gradient as well. I have a short example, a small example here, just to show you how this works. Okay, say you have again two states, S1, S2. Episode starts as S1, take an action A, S2, action A, terminal, okay? Or rather, take some action A, then go to S2, take some action, go to terminal state, okay? Reward, if you take A in S1, in S2, reward is 1. Otherwise, it's 0, okay? So basically, from S1 to S2, you don't have any reward, okay? Discount factor is 0.9, okay? Right, so here we are stored in tables, and for actor, the policy gradient method, what do? You use something called softmax, right? To get the probabilities of the actions from preferences, okay? Okay, here you see the initial values are non-zero for S1 and S2, VS1, VS2, okay? And these are the probabilities of, these are the preferences rather, okay? So here you have policy A, so the probability of taking A in S1 is 50 and probability of taking A in S2 is 50, okay? So first episode, choose A in both states. So if you compute your value functions now, because the initial reward that you're getting from S1 to S2 is 0, it will be 0 plus discounted factor times your estimate already initialized S2 value, which is 0.2. So your error now is 0.132, meaning that the action that you took is bad, not good. Okay, so here you go back, based on this delta you will update your VS1, okay, which is the critique part. Clear? You updated the value function now, so the value has decreased from 0.5 to 0.468, right? And now for the actor part, critique part did the value updates. The actor part will now do the update of the action probabilities, the policy, right? So here we already talked about how we got this, right? 1 minus pi and minus pi, okay? So here say for S1A, you update the parameters, you take 1 minus pi of AS1, which is 0.5, we already know. So here this says this is a negative value, implying you'll have to decrease this. That is, decrease the probability of taking A in S1, okay? This would in turn mean that you increase the probability of B in S1. Why? Because its probabilities are complementary, right? If one decreases, the other has to increase, so as to ensure that the total sum of those probabilities is always 1. Okay, so now if you convert those preferences into probabilities, you will get the probability of A as 49.2% and the complementary of that would be 50.8%. Okay. Similarly, now in S2, you again choose A. Okay, the immediate reward that you're getting is 1 and its terminal, so 0, the value of that, right? Minus VS2, the initial estimate was 0.2. Okay, here, okay. So you get a delta of 0.8. So is the action good or bad now? Good. Why? Because it's positive, right? See, positive feedback, better than the critique expected. So this way you will have to update the value function of S2. Now the value of S2 will increase, right? And you see that here, the critique does indeed increase the value from 0.2 to 0.28. Okay? Similarly, what the actor will do is it will increase the probability of taking A in S2, right? And that's exactly what it does, okay? You see here, see A S2, it's a positive number, so yes, it has to be increased. So now after first iteration, your probabilities of your value functions have been updated. This has decreased from 0.5 to 0.47, whereas for S2 it has increased from 0.2 to 0.28, okay? And the probability of taking action A in S1 has decreased, whereas the probability of taking action A in S2 has increased. Clear? Clear? Okay. So this was the numerical example. Now I will.
When we will end the iteration, like when the advantage value will be 0 means
You tell me when will we end the episode. You'll end it at advantage 0? Or advantage positive, advantage negative, when will you stop? Exactly. So which would in turn mean when the value functions or the probabilities have stopped changing, you stop. That is when you have achieved convergence. Clear? Yes.
That delta is that is basically TD, right?
TD, yes. Which would also be the advantage function, because advantage function was GT minus V pi. And for TD as well, we are taking GT as this bootstrapped value, which is nothing but GT if you run it for the full episodes, right? Okay. Yes, we talked about policy gradients being more suitable for continuous states and continuous actions in spaces, but still you remember we have something called the softmax there, where you have E theta by E sigma theta, okay? And it includes some other terms. So this would mean that there is a summation here. Summation implying that you need to have some finite number of terms here, or it becomes an infinite series, right? Right? So then how is this suitable for continuous action spaces? Value based, yes, obviously you have a table, so that's why it gets very difficult. It is obvious. In this one, and you can negate this, right? How can you overcome this issue? By using a neural network there, right? instead of this thing, instead of the table, you can use a neural network, right? But again, that still will not be applicable for, say, continuous actions, right? Sorry? For discrete actions, yes, for discrete actions. So even here you have this term, right, which is a summation. Sorry, this term is a summation. So that means you need to have a fixed number of steps here, otherwise the summation will become infinite, right? So how do you overcome that? You, instead of softmax, you use something called, sorry, go on. All of those will involve summation, right? So you simply use Gaussians. You use Gaussians, okay? Now how? We'll come to it, okay? Okay, I just wanted to give you an overview of what's to come. But here, now we know that we have two kinds of functions, right? In fact, three functions, right? One is the value function, the other is the policy function, the third is the, no, I mean value functions will include state and action functions, right? And then you have the policy functions, which is the policy itself, and then the third one was, even I forgot. What was the third? Okay, yes. VQ? No. I forgot. Okay, sorry? No. Okay, any which ways, you will have to basically now have functions that you want to approximate, right? So these functions, when they become continuous, you cannot use normal tabular methods there, right? You need some kind of more advanced or complex methods, right? Exactly here steps in neural networks. So when you use neural networks as function approximators, okay, for either the policy itself or the actor critiques, or the value functions that you have, you can use neural networks, and when you use this, reinforcement learning becomes deep reinforcement learning, DRL, okay? Because now your functions are approximated through this neural networks.
Continuous in the model and the environment and the action rules, right?
Sorry?
You need continuous in, when we're saying we have continuous action and also
Observations.
Yes, I'm talking
Yes.
about both of them.
No, even if one of them is continuous, you still need deep reinforcement learning, right? You cannot use, say if you have continuous actions, you have action A1 and A2, which is say 5 degrees and 10 degrees. Between that you have infinite numbers. So that's continuous, right? Even if you have, say, discrete spaces, right? Say you have blocks, but you want to move in a continuous action, you cannot, right? So you need, for either of them, for continuous spaces, you need deep reinforcement learning. Clear? So here, like we already talked about, you will have parameters of the policy theta, parameters of the value function as W, okay, which corresponds to the parameters of the neural networks, which would be for actor and critique, right? W will be for critique, theta will be for actor, okay? Conceptually, nothing changes, right? You're still approximating in the same way. You take the TD error, that will be your loss function. But here, instead of simple numbers, you will have vectors of numbers, right? And if you're using neural networks with nonlinear activation functions, even that nonlinearity will come into play, right? So you will use parameters here, W and theta, as you will see, for value function and for policy approximation, okay? Okay, now comes this part. So now you cannot use, okay, you can, in fact, if you have discrete actions, you want to have, say, continuous states, you can use this, right? But then this is, for continuous actions, this is not applicable. For continuous actions, you can use something called Gaussian functions, okay? What a Gaussian function is, it can be parameterized by two terms called the mean and the variance, okay? So it takes a shape of a bell. Sorry, this is a very bad Gaussian function, like this, okay? It takes a shape of a bell, okay? The mean corresponds to the highest value, and then you have the standard deviations. Okay, as you go away from the mean, the value decreases. Okay, so for a function for which the variance is 0 and mean is n, how will the graph look like? Yes, that would mean it is simply a impulse function, right? For rest everything it is 0, all the values lie on the mean, right? This is exactly how we do. So when we are using continuous action spaces, right, what happens is the neural network will output you this values, the sigma, the mean and the variance, right? If you want it to be deterministic, you set the variance to be 0. That way all other action probabilities have gone. So basically here on the x-axis you have actions, and on y-axis you have the probability of that action, right? Clear? Action on the x-axis, probability of action on the y-axis, right? So you know that for this state you will be like, okay fine, I take this action, right, with if it is a curve like this, say with 60% certainty I'll take this one, but remaining 40% I can either take this or this, right? Clear? You don't have to say you have a discrete space like this. Okay, your action is here, your action is here, so anything in between you will have to interpolate, right, which might not always be the best thing. So that's why this is the continuous part for it. Clear? Okay. However, one of the assumptions that we talked about when we were talking RL is for not being lost in a local minima is the assumption that, what's the assumption? How do we not get stuck in the local minima? You people asked this multiple times and we talked about it many times. Sorry? Epsilon method is just for exploration, but why are we doing that exploration? Even with exploration, there was one thing that we had to do. Come on, give it a try. What is one of the most important assumptions in RL that we did so that we made sure that we weren't stuck in a local minima?
The function has one minimum only.
Yes, obviously, but then there might be, any function will have one global minima, right? But then there will be other local minima. So if you're stuck in that, how do you come out of that and reach the global minima? No? Exploration, you're getting close, but why are we exploring? Exploring is a reason. Like, what did we want to get out of that exploration? We wanted to make sure one thing. Why are we exploring? Sorry? And remember, I keep repeating this again and again, that you have to run the episodes or do enough number of steps that you are taking. Exactly, yes. So here the assumption is that you will visit every state and take every action in that state infinity times, right? So that is one of the most important underlying assumptions that we have for RL in order to guarantee the optimality of the policy. However, with a continuous state space, can you imagine doing that infinity times for every state and action?
Even if it's discrete, like how can you achieve an infinite number of times?
No, say suppose, yes, okay, that's the point. No, I mean infinity in the sense you do it enough number of times such that you can see that the values have stopped changing.
Right, that is convergence. That is not necessarily doing it an infinite number of times.
But we cannot achieve that by infinite. It doesn't mean infinite. It tends to infinity basically. So you have to take a lot.
Converging.
Yes. The other error is the approximation error itself, okay? Because of the model of the neural network, say your model was not, the neural network that is not deep enough, or doesn't have enough activation functions, or the activation functions are not good enough. Then the values that the critique or the actor for that matter compute, okay, the value functions and the policy might be not very accurate, right? So there will be some bias in it. Clear? And the other is bootstrapping, right? Because you're estimating and then the estimate involves another estimate, right? Which could cause an error, okay? However, there are some tricks that are used in reinforcement learning to overcome these errors, okay?